Uh, we'll first cover some basic aspects of negative feedback amplifiers. That is, we'll see how to design a negative feedback amplifier for a given gain. Then see how we might be able to realize it in circuits. As you know, we have transistors which essentially behave like voltage controlled current sources, and everything that we make have to be realized using voltage controlled current sources. That's what we'll look at. Now you'll see that under some conditions, you make a negative feedback loop and it's not stable. It just becomes an oscillator. We'll see what those conditions are. We are not so interested in making an oscillator as we are in making an amplifier. So the idea will be to prevent them from becoming an oscillator and keep them stable. And we'll see how to stabilize them, the criteria for stability of negative feedback systems. And also once you have a realization using transistors, how you can make it stable. Okay. Then we'll look at some aspects of feedback around transistors. These are basically little circuits which we use routinely in ICs, but which are usually not thought of as feedback systems in many books. We'll look at those things. And then we'll deal with we'll just show transistor level schematics of CMOS op amps of 1, 2 and 3 stages. And we'll hope to also discuss the effect of nonlinearity in a negative feedback amplifier. That is, whatever amplifier you use in a negative feedback loop, if it's nonlinear, what happens? And we'll do a couple of case studies. One of them is a fifth order active RC filter. It uses certain type of op amp which is not commonly used. That's what is special about it. The other thing is lead lag compensation. I call it lead lag compensation. It's basically the op amp amplifier topology that's very commonly used both in integrated and discrete systems. So that's what makes it somewhat interesting. Now there is a lot of material here. It's not necessary that we go through the whole thing. We'll just go through whatever is comfortable for you guys. So feel free to interrupt whenever you don't understand, so we can just discuss it right away instead of cramming a lot of material which you don't understand. Okay. So with that, I'll get started. I'll deal with the first topic, and then Shanthi will take over and deal with rigorous aspects of stability analysis. Now this is our goal. We want to realize an amplifier of some gain K using negative feedback, and we would like to do it as accurately as possible. That is, when I say I want a gain of 2, I want it to be exactly 2. And also I want it to operate at a high speed. That is, I apply an input with any rate of change, it should really amplify it without modifying it in any way. Okay. What is negative feedback? We are all familiar intuitively with the idea of negative feedback. Let's say you are playing some audio and it is too loud. What do? You are of course hearing the audio. Essentially you are sensing what is coming out of the speaker, and then you keep rotating the knob until the volume becomes comfortable to your hearing level or your taste. Okay. Similarly, if the volume is too low, you go on increasing it. And we do it in many other cases also. So let's say you are driving a car and then you want to go at 50 kilometers an hour and you are going at 30. What is it the natural thing to do? You hold the accelerator pressed until the speed increases and becomes 50. Okay. So this is what we know about negative feedback. Essentially, you sense what the output is. In one case, it could be the output volume. In other case, it could be the speed, which you read through the speedometer. And then you take some corrective action until that output becomes what you want. Okay. So this is a block diagram that depicts this action. Essentially, when you sense the output, what I'm saying is you are looking at the speedometer. That's all. And then you compare whatever speed you want to go to with whatever is on the speedometer, and then you either increase or decrease the speed. Okay, you either brake or accelerate. Now also, another thing is important. Let's say you are going at 50, you want to go at 50, and you are going at 20 kilometers an hour. You press down the accelerator pretty hard. You want to go at 50 and you are going at 48. You don't jam the accelerator. Maybe some people do, but you shouldn't. You should do it a little softly, right? So that's what the last bullet says here. The drive the amount of drive you give to the car is proportional to the difference. You don't go and always jam the car, or at least you don't, if you want to go to 50 and you are at 10 kilometers an hour, you don't just gently press on the accelerator. That's not an efficient way of doing it either. Okay. So what we'll try to do is to make an amplifier using the same principles. Okay. To do that, we will need to know what the behavior of each of these blocks is, right? Especially how in the case of a car, the speed responds in some way to your drive. We want to know what that is, and then once we know that, we can translate everything to electrical domain, either voltages or currents, and make our negative feedback amplifier. Of course, we'll do everything with voltages, but without loss of generality, you can do the same thing with currents or in any other variable, in any other domain as well. So what we want to know is the behavior of this particular block that says increase or decrease S0. Okay, it's not good enough to say increase or decrease. We want to say how it increases or decreases. So for this, it pays to look at a case. Let me first describe this block diagram. This the first one is a comparison block. It looks at the desired speed SI and the actual speed, which is sensed by looking at the speedometer, and its output is the difference. Okay, SE is SI minus S0. Now, it pays to examine a case where this SE is constant. So let's say, for instance, that the car you are driving has a stuck speedometer. It keeps showing 30. What happens? You will just keep the accelerator at one particular level. You think that the speed is 30 because the speedometer is showing 30. And what will happen to the speed? What happens to the actual speed of the car? It will go on increasing, right? It will go on continuously increasing. That's what this is showing here, the graphs here. So let's say the difference was the blue line. That is, the speedometer was stuck at 48. Then you would have pressed the accelerator gently, and the speed will go on increasing gently, like this blue line. Or it is like the red line. Let's say the speedometer was showing 30 and you want to go to 50. You press down on it hard, and then it ramps up faster. Okay? Is this clear? So, yeah.
Whatever you said about this feedback, I think in general, it's concept of feedback, I believe.
Yeah.
If you say there is this concept of negative feedback, what is the concept of positive feedback then?
No, negative feedback means that you drive it in a direction where the error becomes smaller, right? You sense the error and you drive it in the opposite direction.
My belief is the output with a negative feedback falls back.
What is that?
Output with a negative feedback
No.
come down.
No. It doesn't always come down. There is some desired level of output. It can go up to that or it can come down to that. The idea behind negative feedback is to reduce the error, right? That is the heart of negative feedback. You measure the error between what you want and what you have, and you reduce that to as small a value as possible. That's the general idea. It can be implemented in many ways.
And how do you able to tell positive feedback?
No, positive feedback tends to drive the error up. It's not the output itself. The output can go up or come down, but the error between what you want and what you get can it goes up in case of a positive feedback and comes down in case of a negative feedback. In an ideal negative feedback system, that error is 0. Okay. Now, this is what happens with a constant error. If you have a large error, then the output ramps up quicker. If you have a small error, it ramps up smaller. So it's clear what block we need here, right? If this is the left graph is the input and the right one is the output, what is that block? It's an integrator. So we need to use an integrator. That's all. This is what you are mentally doing when you accelerate a car or something. Okay. You will respond to the difference and then you keep ramping up the speed or ramping down the speed when you brake. Okay. So essentially we need an integrator. So once we establish that we need an integrator, we can make an integrator in the electrical domain also. Let's say we know how to do that. We know how to integrate a voltage to get another voltage. In that case, this is how we would try to make an amplifier. Okay. What is the input? It's some input voltage Vi. The desired output is some K times that. And we have to compare this K times the input KVI and the actual output V0. This gives me the error. And this error I have to integrate. Okay. And what will happen? the integrator will keep driving it in one direction or the other. Let's say, for instance, kVi is more than V0. So, which means that this error here is positive. Basically, that means that V0 is too small, right? The integrator will keep on driving up the voltage. And when will it stop? When will the integrator reach steady state? When its input is 0. So, the kVi has to be exactly equal to V0. Okay. So, that's how it builds up to steady state, and at steady state you get exactly V0 equals kVi. Okay. So, that's the general principle. Of course, you have to implement this correctly, because you can't really take kVi and compare it to V0, because if you already had kVi, you would not be building another amplifier, right? So, you have to do something else, but it's very easy. What you do is, instead of comparing k times Vi and V0, you compare Vi and V0 divided by k. That's all, because division is free, right? At least it doesn't take as much effort as multiplying up a voltage. So, I have my output voltage V0 here. I pass it through a resistive divider, which gives me V0 divided by k at this point. And I compare that to the input Vi. So, Vi minus V0 by k is some error. It's a measure of how far the output is from the desired value. Then I just integrate it and use the integral to drive the output. Okay. So, again, the only way the integrator will reach steady state is when its input is 0. Otherwise, the output will keep on going up or keep on going down. So, output is 0, which means Vi equals V0 by k, which means V0 is kVi. Okay. So, I have my negative feedback amplifier. Is this okay? So, before we go further into this, this is sort of the heart of every negative feedback amplifier. You will have something that behaves like an integrator. Now, because of a lot of practical reasons, that block can have more sophisticated behavior, but in some reason it turns out that it behaves like an integrator. Okay? Yeah, I will come to that. Now, the integral is integration with respect to time. To keep the input and output dimensions the same, I need to have some proportionality constant, which has dimensions of frequency. I'll explain what that means shortly. So, what we'll first do is look at the behavior of an integrator, and then look at the detailed behavior of this in a mathematical way. But for now, it should be clear that if V0 happens to be different from kVi, the Vf, which I call the feedback voltage, will be different from Vi. Okay. So, which means that Vi will drive it in some direction. If it is more, it will reduce it. If it is less, it will increase it. So, the only way it will reach steady state is when V0 is kVi. Okay. Now, this is showing the behavior of just the integrator in the time domain. Like, yes, this omega u is a proportionality constant, so that I get voltage to be some frequency times integral with respect to time. Okay. So, this omega u is a parameter that describes the integrator. What does it mean? Let us say we have I have plotted the output voltage with respect to time, and let us say the input is 1 volt to the integrator. What will happen? The output will be omega u times 1 volt times t, right? So, that means that omega u represents the rate of change of the output. The larger the value of omega u, the faster the output. Okay. For instance, if I apply 1 volt input and omega u happens to be 10 to the 9 radians per second, then the output will ramp up like this. Okay. In every 1 nanosecond, it will ramp up by 1 volt. Okay. And if omega u is smaller, 2.5 times 10 to the 8 radians per second, in every 4 nanoseconds, it will ramp up by 1 volt. So, omega u simply represents the speed of integration. The larger the value of omega u, the faster the integration. Okay. Now, as you can see, this will have a bearing on how fast the amplifier will reach steady state. Okay. So, you can have two kinds of drivers. Some people drive hard and some people drive very softly. They don't want to press down on the accelerator. Or you can have different types of cars which will have slower or faster response. But both of them can reach the desired speed, right? Especially if it is a modest 50 kilometers an hour. Okay. So, you can reach it slower or faster. That simply depends on how fast you press down on the accelerator. And this omega u is a measure of how fast the accelerator is being pressed on. Okay. And the higher it is, the faster the amplifier, as we will see. Now what will happen in an amplifier? Earlier I examined a case where the input to the integrator was a constant, okay, but the input will not be constant. What happens is, let's say you start with some value of V0, which is different from K times Vi. So initially Vi minus Vf will be of some value, and the output of the integrator starts ramping up corresponding to that value. And as it ramps up, Vf itself increases, which means Ve decreases. So the rate of ramp also reduces. Okay, and this is again similar to every other notion of feedback that you know. You press down hard and then you just ease back on the accelerator, all that stuff. Okay, the error keeps on reducing as the output keeps building up, and then because of that, the rate of change of the output also keeps on reducing. Okay, we will find a mathematical form for it, but this is what you expect. If the input is this blue line, ideally you want, in this case I have taken a gain K of 4, the input is 1 volt, I would want the output to be 4 volts. But initially, let's say the output is 0, okay. So that means that the feedback voltage is 0 and the output starts ramping up at a high rate, okay. And as the output ramps up, the feedback voltage also ramps up, that's the green line here, and the error starts reducing, the red line is the error, okay. So the output ramp slows down, and finally when it reaches 4 volts, the output stops ramping up, okay. This is again very familiar curve from a negative feedback system, but I am just showing it in a different way. Now we can evaluate that mathematically, okay. Once we understand that the rate of change slows down, we can also do that mathematically. What I have shown here is, again, this Vf, the feedback voltage is V0 divided by K, okay. So the input to the integrator is Vi minus V0 by K, okay, Vi minus V0 by K, and this is what is integrated to give you the output. Now instead of casting it as an integral, I have shown it as a derivative, that is the derivative of V0 is omega u times whatever is at the input, okay. So this is the equation. So if you solve this equation, you can find out mathematically what happens, okay. And this is a simple first order differential equation, and the solution is shown in the following line, okay. The output will turn out to be kVi, that is the desired output, times 1 minus some exponential, and also it depends on the initial condition. You don't know where it starts from, okay. Depending on how you operate it, then it could start from above the desired value, below the desired value, 0, not 0, whatever, okay. And that is multiplied by some exponential, okay. Now this is something that must be very familiar to you as a force response and natural response of a first order system, and that's what it is. And you can clearly see that whatever component is contributed by the initial condition, it dies out eventually. It will have some contribution for sure, it will eventually die out, and this is due to the input. This is what you want to reach. It reaches 1 minus something, and after a long time the exponential becomes 0, so you simply get kVi, okay. So it approaches kVi as you wait, okay. You have to wait for some time, okay. Nothing happens instantaneously, right. And that's what is shown graphically here. The blue line is the input and this dirty green line is the output. Again, I have taken a gain of 4. So if I apply 1 volt, I should have got 4 volts. Ideally, maybe I would expect the instant I apply 1 volt, I will get 4 volts. But in reality, things take time. So what happens? Let's say the output was initially at 0, starts ramping up, and the rate of ramp keeps on slowing down, and it follows it like this, okay. Or it could start from something higher also. It could start from 5 volts. Then in fact it starts ramping down, and the rate of ramp down slows down, and it goes to 4. Anywhere you start from, it goes to 4, okay. Eventually you simply have to wait long enough and you get your ideal output, okay. Any questions so far? That's correct. We'll see the significance of that. The time constant, as you can see, is related to omega u, which is a parameter of the integrator, and also k, the gain that you are trying to realize, okay. We'll see how it comes about soon. No, omega u is a measure of speed. If you want it to go faster, let's say I wanted it to go something like this, then I would have to use a larger omega u. Or if I could allow more time, I could use a slower omega u. So omega u is primarily a measure of, it is only a measure of speed actually. Okay. Now we'll do some more sophisticated analysis. What we have done so far, if you observe, is that the input has been held a constant, right? We applied a constant 1 volt and see what happened to the output and so on. Now this is fine, it's of some value and it allowed us to analyze the system in the time domain and it gave us some intuition, but this is not what we always do, right? The input can be varying and most of the time the interesting inputs are varying in an amplifier. Now we would also like to see what happens when the input is varying. Now if the variation of input is some arbitrary fashion with time, it becomes very hard to analyze. You can solve it, you can solve the differential equation numerically, which is what simulators do. But what we are more interested here is in getting some intuition on how things behave, right? So again we resort to the old technique. We assume that the input is some sum of sinusoids, right? And then once we analyze one sinusoid or sinusoids of different frequencies, we can put them together and then find out what happens when you put all the sinusoids simultaneously. Okay. And to do this analysis for sinusoids, we resort to the frequency domain as usual. Okay. This is again something that is familiar. We use Laplace transforms and we substitute S equals j omega and that corresponds to sinusoids of frequency omega. And this is what we use for analysis, right? So before that, I described what an integrator is in the time domain. Let's see what the integrator is in the frequency domain. What do I mean by that? First, on the left side, I have this transfer function of the integrator, which, as you well know, is omega u by s. If the integrator in the time domain is described as omega u integral, that will be omega u by s. Okay. Now, on the right side in the plots, I have shown the magnitude and phase of this function when s equals j omega. Okay. This is what corresponds to sinusoidal frequencies. Now what happens if you substitute s equals j omega? For the magnitude, I have omega u by omega. Omega u is some constant and I have basically an inverse proportionality to frequency. Okay. So the magnitude reduces as the frequency increases, and on a log scale you well know that it follows a straight line with a 20 dB per decade slope. Is this familiar to everyone? The Bode plot of an integrator? Okay. Now, what is omega u after all? If the frequency, if s is j times omega u, the magnitude of this is 1, right? So, here we can see a different type of significance of omega u, that omega u is the frequency at which the gain magnitude becomes 1. So, the red line 1 or 0 dB, okay? The red line corresponds to 10 to the 9 radians per second. So, at 10 to the 9 radians per second, it is crossing the 0 dB line. Similarly, if omega u is smaller, this is what happens, the blue line, it moves down. Okay, it simply moves parallel to itself. It's always at 20 dB per decade. And the phase is always minus 90 degrees. Okay, because this is an imaginary number, omega u by j omega. Okay. So this gives you the significance of omega u in the frequency domain. And what does higher omega u mean here in the frequency domain? It means that it has higher gain for all frequencies, right? The red curve is above the blue curve always. Okay. So higher omega u means faster ramp up in the time domain and a higher gain in the frequency domain. Is it okay? Yeah. Yeah. No, it's a constant. It's a constant. No. Vi is not changing. Vi is the constant 1 volt. Okay. VO is changing. That's all. So this is a quick summary of the integrator in time and frequency domains. It's faster in the time domain and a higher gain in the frequency domain. Okay. Now we analyze the whole negative feedback amplifier in the frequency domain, just like we did it in the time domain. That was useful for constant inputs, and this is useful for sinusoidal inputs. So again, we turn the differential equation into a Laplace in the Laplace domain, and we get this omega u by s Vi minus V naught by k. Okay. And what is the result we have? V naught by Vi turns out to be k divided by 1 plus s by omega u by k. Okay. Now, what does s equal to 0 correspond to? DC. Okay. If we substitute s equal to 0, we get k, which is what we wanted, right? We wanted to realize an amplifier of gain k. Now, it does behave like an ideal amplifier, but you see that this amplifier has a pole at omega u by k. So, what does it mean? The magnitude response will be k for low frequencies, and for high frequencies it simply falls down. Okay. So, what it means is, we would like an amplifier that has a gain k for all frequencies, but it's not so. It has a gain k for some limited range of frequencies, and that range is given by this omega u by k, roughly speaking. Roughly speaking, we can say that for frequencies below omega u by k, it behaves like an ideal amplifier, and beyond that it doesn't. Okay. So, in the frequency domain, omega u simply puts a limit on the range of frequencies where it behaves the way you want. That is, behaves like an amplifier with gain k. Any questions on this? And the left plot is the pole 0 plot, which shows a single pole at omega u divided by k, minus omega u divided by k. Okay. Now, I am interested in sinusoidal inputs, so I substitute s equals j omega, right? That's what I have done here. And again, these are familiar expressions for first order systems. And DC gain is k, as we expect. DC gain in time domain, what does DC gain mean? You wait for a long time, what happens? That is the DC gain. Okay. You apply a constant input and wait for a long time, that's DC. Okay. And one thing you see from this expression, the expression for magnitude is that when omega equals omega u divided by k, the gain becomes k divided by square root of 2, or 3 dB smaller than k. So that we define to be the bandwidth. Okay, 3 dB bandwidth. Now, the significance of bandwidth is pretty clear. I've taken a low frequency signal, low frequency sinusoid, that is the green signal there, and passed it through this amplifier of gain 4. Okay, sorry, blue is the input, not the green one. Blue is a sinusoid of 1 volt amplitude. I pass it, and I should get the green one, which is simply 4 times this. But what do I see? I see the red. What does it have? It has a gain almost equal to 4, right? The amplitude is very close to 4, but it has a delay. Okay, this is a consequence of our implementation. We make it with an integrator, and everything has a delay. Okay, I can't say 50 kilometers an hour and expect the next instant the car to be at 50. Right? It takes some time. So similarly, there is some delay, but the gain is nearly 4 for low frequency inputs. What happens for high frequency inputs? Again, I have applied the blue signal with 1 volt amplitude. I expect the green signal with 4 volts amplitude, but what I get is the red, which is nowhere near 4 and nowhere near aligned with the green signal. Okay, there is a large phase shift and a large attenuation. This is what happens for high frequencies in every negative feedback amplifier. So what you should appreciate is, yeah, we want to make an amplifier of gain 4, but you can't make it for all frequencies, right? There will be some limitation or the other, simply because of delays in the system. Huh? Well, yeah, you can always find use for it. That's the beauty of engineering, right? If something is, it's not a bug, it's a feature. So you can always turn a bug into a feature. But since our goal now is to make amplifiers, we will say this is a bad case. Okay. Maybe your goal is to make a filter, then this is a good case. It is filtering out the signal, right? So, but for now, we will try to make amplifiers. So even instability is a good thing. You can say you try to make an amplifier and then it oscillates, and then say, hey, here is the oscillator, it's $100. So to summarize, what have we done? We integrate the error Vi minus V naught by k to derive the output. And what happens then? The steady state is ideal when the input is constant. Okay, because the steady state is reached only when the difference is 0. Now for slow inputs, that is slow sinusoids, the output is nearly ideal. That is, you get the desired gain, but there is a delay, k by omega u. That is also related to this omega u by k. That is another thing you have to keep in mind, right? If you started with a high omega u, you would get a small delay. Okay. And the output is attenuated for fast inputs. We are not too concerned with this now. At least we don't want to have any use for this one. Okay. So this is a quick summary of the amplifier we have been able to design. Now let's see the effect of different parameters on the system. Right now we have only 2 parameters. In fact, the gain k is a specification. Besides that, we have one parameter omega u. Okay. What is the effect of omega u? What do you think it is? Been saying all along that it is related to speed. So let's say I make the same amplifier of gain 4. Okay. And apply a constant input of 1 volt. That is what is shown on the left side. The output should be 4 volts. Now omega u can be any value. Let's say I take 1 gigaradians per second. Then it follows this blue line, ramps up and reaches 4 volts. Let's say omega is 4 gigaradians per second. Does the same thing but much faster. Okay, so that's the pretty obvious difference. So in time domain you will see a faster response. What do you see in the frequency domain? This is the upper plot is showing the gain magnitude. And this dirty green line should be the gain. It should be 4 for all frequencies, but we know we can't have it. If I make this amplifier of gain 4 with an integrator whose omega u is 1 gigaradians per second, it's constant up to here and then it falls off. Okay. If I do it with 4 gigaradians per second, it is constant for a wider range of frequencies and then it falls off. Okay. So this is the obvious thing. So this comes from the specification. If someone says you have to respond fast, you choose a high omega u. If your slow response is okay, you choose a small omega u. Okay. Or similarly, the spec could be given in a frequency domain. You have to operate with signals up to 1 gigahertz. That gives you some omega u. 100 megahertz gives you some other smaller omega u. Okay. No. No. Yeah. No, there is no tweaking here. It is omega u that is doing the tweaking, right? There is no other tweaking. If you think about it, your acceleration and deceleration, that is done by this integrator, which is omega u. It is like you are doing it faster or slower. Now we have assumed that there is no other delay in the system. Now if there are other delays in the system, things might get complicated. But right now what is doing the tweaking is this block, which has a parameter omega u, which is basically related to the speed at which you tweak. Okay. Anything else? Yeah. Yeah. Yeah.
I think we should call it as a low pass filter only because the integrator, when it acts as an integrator, the phase shift is 90 degrees.
That's right. So the integrator itself has a phase shift of 90 degrees. When you enclose the integrator in a feedback loop, the net system has a different phase shift. No. See. No, I think you're. See, what I'm calling as an integrator is this block. What I'm plotting is the response between here and here. Between VE and VO, it is perfectly an integrator. Between VA and VO, it's not an integrator. It's not supposed to be. It's supposed to be an amplifier. Okay. Now, because of the limitations of the integrator, it doesn't behave like an amplifier in some region. Okay. So I never said that between VA and VO, it's an integrator. Between VE and VO, it is an integrator. And as far as we are concerned now, it is still a perfect integrator. Okay. No, it is a low pass filter. Yeah. No, omega u is a constant. In fact, if that is a function of time, it becomes some kind of time varying system, and we can't even represent such a thing with a Laplace transform, right? No, omega u is a parameter of the integrator, right? It has nothing to do with the voltages that you apply to the integrator. Okay, omega u is a parameter of the integrator. Maybe you're a teenage driver and you always ram hard on the accelerator, or maybe you're 60 years old and you always go slow. That is omega u. Okay, that's your age, right? In this case, of course, the age is smaller means you go faster, but besides that, it works, right? Okay, so higher omega u means either faster response or the desired gain over a wider frequency range. Now we can also see the effect of K. Now K is a spec, right? You are asked to make an amplifier of gain K. Now the interesting thing is, let's say you already made an amplifier of gain 4. Now when you say gain, someone says make it for gain 2, you're not going to sit and redesign the whole thing, right? You will try to reuse the blocks from the previous design. So what will you do? You simply change K, which is to say, you simply change this resistor. The only thing that depends on K here is the resistor value, right? Let's say you do that and let's see what happens. What do you expect? So, if you reduce the value of K, it reaches steady state faster. And this we had seen from the expression as well. The time constant was related to K by omega u. Okay? And the bandwidth was omega u by K, which means that the range of frequencies over which the gain is constant is smaller for a higher K. Okay. In fact, from these two plots, you can see that the later part of the curve is the same. So you'll again see the reason for this, but that's what happens. Okay. Omega u is the same in this case. No, only K is varying in this case. We'll just make this observation that for higher K, it becomes slower, and we'll see what to do, how it comes about afterwards. Okay. It comes out of the expressions, but we'll see some intuitive explanation as well. Now, this is just an example of how this omega u comes about, because you are usually given the specs. So, for instance, I won't work through it in detail, but let's say you are asked to make an amplifier of gain 4 with a bandwidth f3 dB of 100 megahertz, which means in the radians per second, it is 2 pi times 100 mega radians per second. So, for this, you will need an integrator with omega u, which is 8 pi times 100 mega radians per second, if you want to make this. Okay. Then you can try and go and design the integrator. Okay. If you want to meet the spec, you have to determine omega u. That's how it works, right? Similarly, the spec could be given in time domain, which is to say, you want to make an amplifier of gain 4, and it should settle to 99% of steady state in some time, 20 nanoseconds. And that turns out that you can again, from the expressions, figure out how much time it takes. And it takes, the omega u required is almost 1 gigaradians per second. Okay. So, from the spec, you can figure out omega u and then build the amplifier. This clear? Now, let's examine this feedback system a little more. So far, we have done some intuitive stuff to get our feedback system, and then seen how it behaves in the time and frequency domains. Now, what I have put down here is the block diagram of the classical feedback thing that you see in the control systems textbook, right? With G in the forward path and H in the feedback path. Now, what is the gain of this? V0 by Vi? G by 1 plus Gh, as I have put down there. Now, I'll cast it in a slightly different form. I will factor it out 1 over H, and it becomes Gh by 1 plus Gh, and I again divide numerator and denominator by Gh, and I get something like this. Okay. 1 by 1 plus 1 over Gh. Is this clear? The second form is obvious? Yeah. Now, it's interesting to see what happens to this when Gh is much more than 1 and Gh is much less than 1. When Gh is much more than 1, the second term in the denominator is negligible. You don't care about the phase. If the magnitude of Gh is much more than 1, that's enough to make this term negligible, right? Is this clear? I don't really care about the phase of that thing. So, where the magnitude of Gh is much more than 1, the gain is 1 over H. Okay? What is so special about this? Depends only on the feedback part. And when 1 over Gh is much less than 1, okay, the second term is It is in fact the second term that is much larger, right? In fact, it's easier to see the first form of the expression, this one. If magnitude of GH is much less than 1, I simply ignore this. I say the denominator is 1. Is that okay? And V naught by Vi will be equal to G. Does it make sense? Why? What is the meaning of this? How did it go from being G by 1 plus GH to just G? We know mathematically what happens. If the absolute value of GH is very small, this is what you get. Essentially what happens is that this GH is a measure of feedback, right? You apply something here and how much comes back is GH times that. If feedback is very small, what happens? I simply cut off the feedback, that's all. So it goes through G and you get G times Pi. Is this okay? So this quantity GH is a very significant quantity in the study of feedback systems. Now if it is very large, the system behaves in one way, and that's usually the way, that is the desired behavior. And if it's very small, it behaves in some other way. Okay? We'll again see this in more detail. The feedback is effectively broken when this loop gain is much less than 1. Okay? So essentially, having loop gain very small is like not having feedback. Okay? That's why simply, if you had an amplifier G, you could get G times Vi simply by applying Vi to G. That's all. Right? Is okay? So that's what is happening here. Now, please keep these things in mind that when GH is much more than 1, this factor in particular, 1 by 1 plus 1 over GH becomes 1. And if it is much less than 1, it becomes GH. Right? Okay. So let me maybe write it and show. So we have G by 1 plus GH, which is 1 over H, GH by 1 plus GH. Now let's ignore this for now. This is the significant part, and you will see that it appears in every feedback system. Okay, what appears before depends on how you apply the input and where you take the output, etc., as we will see. But this part, GH by 1 plus GH, which is dependent only on loop gain, appears in the expression for any gain in any feedback system. Okay, and this happens to be approximately 1 when GH is much more than 1, and it's approximately GH when GH is much less than 1. Okay, and sometimes I will call this GH as L, the loop gain. Pretty obvious, I think, why it's called loop gain. All of you must have taken some basic control source. You break the loop, apply some input in the direction of feedback, and what comes back to that broken point is GH times that input. Okay. Any questions? Now let's put our amplifier, the one that we have designed, in this form, in the classical feedback form, and see what happens. On the left side is the amplifier we designed, and if I have to recast it in the feedback form, this is what I get. And I have done it in the frequency domain, right? This G will be the integrator transfer function, omega u by S. And H will be whatever comes back here, right? Vf by V naught. How much is that? 1 by K. 1 by K. This corresponds to the resistive divider, and this corresponds to the integrator. Okay? It's exactly in that form. Okay? Now, what is the loop gain for this? Now, the loop gain is a property of the network. It's not really related to the input. When you measure the loop gain, you set the input to 0, you break the loop somewhere, you apply a test input, and then you see what comes back. Okay? Yeah? Yeah. What do you mean by non-partitionable? No. This doesn't really relate to any of the, I have not even discussed series feedback or any of the 4 categories, right? The bridge feedback or anything can be probably be broken up into this. as a system, maybe you won't be able to identify the circuit in that way, but it can always be done like this. Right? Any feedback system can be reduced to some form where you can identify the loop gain. Maybe it is very hard to measure and simulate and all that stuff, but it is there. The loop gain is there in the feedback system. Okay. Yeah. So that is what we have done here. Now it could be that this block diagram is very complicated, has multiple loops. I don't know. Okay. For now, I have only considered single loop stuff. But it's not right to say that it's applicable only to this one type of series feedback or whatever, right? Because it can have other kinds of feedback which are also applicable to this, which are also, amenable to this type of analysis. By bridge feedback, you mean that in case of an op amp, the feedback comes to both plus and minus terminals of the op amp. Is that? Yeah, that can be very easily reduced to this. It's not a problem. Okay. So in this case, what is the loop gain? Let's say I break the loop here, okay, and I apply something, and I have these two blocks. I'm not going to write it down because it's so simple. I get omega u by s times 1 by k. That's what comes back, right? G is omega u by s and h is 1 by k. So L is omega u by ks. Yeah? See, right now we are discussing it at the block diagram level where there is no loading. So we'll later see what to do. We can discuss what happens with loading and so on. Okay. It's not easy to break the loop, but this is a conceptual breaking of the loop that we do for analysis. Okay. If you make a transistor level circuit and break the loop, many things can happen. The loading will change and the bias will change. You have to take care of both. Okay. So it turns out that this loop gain is omega u by ks. Okay. What is the significance of this? What are the frequencies at which the loop gain is more than 1? So what is the frequency at which loop gain becomes equal to 1? Omega u by k. Okay. So if you recall, in all our expressions in time and frequency domains, we had omega u by k appearing. And why it appears is this. This is the significance of loop gain. Right? Omega u by k, I'll call it omega u loop. That is unity loop gain frequency. Okay. And this is the significant part. The unity gain frequency of the integrator itself is of some significance, but mainly for the feedback system, this is what is significant. Now, what is this frequency? Now, I said that the negative feedback system behaves one way when the loop gain is much more than 1, and another way when the loop gain is much less than 1. Now, this omega u by k or unity loop gain frequency is the dividing line between where it is much more than 1 and much less than 1. Not really much more and much less, but we can take it as a crude dividing line. Okay. So it's the dividing line between where it is greater than 1 and less than 1. Now, if you want crude analysis, we can say that where it is more than 1, it behaves ideally, where it's less than 1, it behaves non-ideally. Okay. Which is why when the loop gain is small, that is when the frequencies are below omega u by, when the loop gain is large, when the frequencies are below omega u by k, you get almost ideal behavior. And beyond that, you don't get ideal behavior. Okay. So this is true of every feedback loop. If the loop gain is very large, you will get the gain that you designed it for, and if the loop gain is very small, something else happens. Okay. So I have shown it graphically here. The red line is the transfer function of magnitude, gain magnitude of just the op amp. It has some omega u. Okay. Now the blue line is the magnitude of the loop gain, which is omega u by ks. Okay. So simply the magnitude shifts down by the gain of k of 4. Okay. And the omega u loop is at omega u divided by 4 because this has a 20 dB per decade roll off. Now this term gh by 1 plus gh will be 1 where the loop gain is large, that is this part of the curve. Below omega u loop it will be 1 approximately. And after omega u loop it will simply follow this curve. Is this clear? This is what I showed earlier. So when GH is much more than 1, it is 1. So I'll plot the magnitude of GH, and it could be like this. And this is the 0 dB line, and this is the unity loop gain frequency. Now we can approximately say that below unity loop gain frequency, this term GH by 1 plus GH is 1, and after that it simply follows GH. Okay, that's the curve I have plotted there. Now the closed loop gain is not GH by 1 plus GH, but it is 1 over H times that one. So it simply gets lifted up. In this case, H is just 1 by 4. So the same curve gets lifted up by a factor of 4 on a log scale. Okay. So we get this to be the transfer function. It has k, gain of k up to unity loop gain frequency, and it has some roll off after the unity loop gain frequency. So unity loop gain frequency is the bandwidth. Okay. This is clear? This we'll use extensively later to do intuitive analysis of feedback loops. That's why this should be very clear in your mind. Okay. So you make any feedback amplifier, the unity loop gain frequency defines the bandwidth. Yeah. No. This omega u loop is the unity loop gain frequency. Okay. So that is the bandwidth of the closed loop gain. No, that is okay. That is something. It just happens. It depends on the value of k. It's just a coincidence. The significant part here is this omega 3 dB. Okay. This is for k equal to 4. Yeah. No, this is. Yeah, I'll do that later. So this is what I just talked about. The 3 dB bandwidth happens to be the unity loop gain frequency, and in general, basically in any feedback system, the ideal behavior happens when the loop gain is very large. Okay. Now in our amplifier, the unity loop gain frequency is omega u, that is the unity gain frequency of the integrator divided by k. Now the first thing to remember is it's not always the case. The loop gain frequency is not always omega u divided by closed loop gain k. You have to look at the loop and figure it out. Okay. In our case, it translates to the prototype feedback system directly, and that's why it is like that. Okay. So the thing to remember from here is that wherever the loop gain is very large, you will get ideal behavior that you wanted. Now this is an obvious example of a case where the loop gain frequency is not simply, unity loop gain frequency is not simply omega u divided by k. What I have done is I have taken the same amplifier as before. Okay, you remember this block diagram? And I have grounded this input, and I have applied the input here to the bottom end of the resistor. I think this slide is not there in that. Okay. So it's applied to the bottom end of the resistor. Now, if I translate it to a block diagram, you will end up getting something like this. Okay. Feedback block diagram. You will have a k minus 1 by k in front and a classical feedback loop, which looks exactly the same as before. Okay. It's exactly the same except for this k minus 1 by k. Okay. Actually, it's minus k minus 1 by k. And V naught by Vi turns out to be minus k minus 1 divided by 1 plus S by omega by k. And this you will recognize to be the inverting amplifier that most of you are familiar with. But you see that the denominator is exactly the same. The gain of this is k minus 1, the gain magnitude. But the denominator is the same as before. Okay. The loop gain is still the same as before. So it's not really related to the closed loop gain, but it's related to how the loop is. Okay. The loop is exactly the same as before. What I mean by how the loop is you apply a zero input and look at the circuits, different circuits. If they have the same structure, that means they will have the same loop gain and same bandwidth. Yeah, it depends only on the feedback factor, not on the closed loop gain. Okay. This is because the loop gain and later we'll see the stability are properties of the loop. Okay, it's not related to where you apply the input or where you take the output from. Now, in an electrical network, the input can be anything. It could be voltages at various points, currents at various points, and the output also can be taken from any node or as any node voltage or any branch current. Okay, the basic properties of the feedback loop, like loop gain, don't depend on any of that. It only depends on the loop with zero input. Okay. Now, as you can clearly see, if I have zero input here, it looks exactly like the old amplifier with zero input. Okay. The transfer function depends on the input-output locations. Okay. So this is another thing to be kept in mind. So you have to evaluate the loop gain separately. You can't simply look at the closed loop gain and say that the unity loop gain is omega u by that one. Okay. Is this clear? Now, this is just a quick summary on why I started off the discussion of negative feedback amplifier with an integrator as opposed to a high gain amplifier, which is what is normally done in books. The reason is I find it easier to extend the intuitive notion of feedback. What you do, it takes some time, and that comes out when you have an integrator. When you have an amplifier, there is no concept of delay, right? Everything happens instantaneously. So that is what happens. And also, secondly, like every feedback system will have integrator-like behavior over some range. It has to have it, as we'll see later. Okay. And finally, if you want ideal behavior for all frequencies, you can go either from the ideal amplifier or from this. In case of an ideal amplifier, you set A0 to infinity and it becomes an ideal feedback loop. In case of this, you set omega u to infinity and you will again get an ideal feedback for all frequencies. Okay. So I find that there is not much limitation with this approach, but it brings in the notion of delay and bandwidth right at the beginning. Okay, that's why. So you can give me feedback on whether it worked or not. And now, any questions on this part? We'll go to how to realize negative feedback systems.